Sample dispersity refers to the degree of non-uniformity or variability in the size or properties of particles within a sample. Polydispersity index, PDI, is a measure used to quantify the polydispersity of a specific sample. Though IUPAC has deprecated the use of the term polydispersity index, replaced it with the term dispersity, represented by the symbol D stroke, which can refer to either molecular mass or degree of polymerization. A collection of objects is called uniform or monodisperse if the objects have the same size, shape, or mass. A sample of objects that have an inconsistent size, shape, and mass distribution is called non-uniform or polydisperse. Dispersity provides a numerical value that describes the particle size distribution relative to the mean particle size. A dispersity value below 0.5 indicates monodispersity, whereas values greater than 1 indicate increasing polydispersity. The particles vary more in size. The term polydispersity, or dispersity, as recommended by IUPAC, is used to describe the degree of non-uniformity of a size distribution of particles. Also known as the heterogeneity index, PDI is a number calculated from a two-parameter fit to the correlation data, the cumulance analysis. This index is dimensionless and scaled such that values smaller than 0.05 are mainly seen with highly monodisperse standards. PDI values bigger than 0.7 indicate that the sample has a very broad particle size distribution and is probably not suitable to be analyzed by the dynamic light scattering DLS technique. Different size distribution algorithms work with data that fall between these two extreme values of PDI, i.e. 0.05 to 0.7. The calculations used for the determination of size and PDI parameters are defined in the ISO standard documents. In the field of polymer science, dispersity is employed to measure the breadth of the molecular weight distribution of the polymer. PDI can be defined as MW divided by Mn, where MW is the weight average and Mn is the number average molecular weight. Dispersity is basically a representation of the distribution of size populations within a given sample. The numerical value of dispersity ranges from 0.0 for a perfectly uniform sample with respect to the particle size to 1.0 for a highly polydispersed sample with multiple particle size populations. Values of 0.2 and below are most commonly deemed acceptable in practice for polymer-based nanoparticle materials. Both average molecular weight and molecular weight distribution are the two key characteristics that determine the properties of polymers, and the dispersity is used as a measure of the breadth of the molecular weight distribution. PDI is defined as MW divided by Mn, where MW and Mn are the weight average and number average molecular weight, respectively. The general belief is that a polymer sample with a higher PD would have a broader molecular weight distribution, interpreted by a larger standard deviation. However, it is clear that dispersity yields information on standard deviation over Mn, but not on standard deviation, which is a better measure of the breadth of a distribution curve. Consider two polymer samples having the same PDI, say 2, but with different Mn values, 10,000 and 100,000. Here, the standard deviation of the two samples are 10,000 and 100,000, respectively. It is obvious that although the two polymer samples have the same dispersity, their standard deviations are completely different. By analogy, with two samples having different Mn, the sample with higher dispersity may not have a larger standard deviation. Therefore, dispersity, or PDI, is a measure of the standard deviation over the number average molecular weight, not the standard deviation. The dispersity index serves as a pivotal biophysical parameter, shedding light on the diversity and variability present within a given sample. A polydispersed sample encompasses components of distinct sizes, which can indicate the presence of contaminants, impurities, monomeric units within a polymer, or unbound ligands. Dispersity, or PDI's utility, spans diverse applications, including the evaluation of purification processes, monitoring synthetic polymerization outcomes, quality control in protein characterization, and the quantification of binding parameters between molecules forming a complex.